Well, hello and welcome once again to Doc Onco Physics. Keith Onco here. What we're going to be doing today is taking a look at the magnetism lesson, and this is part 3. So this is part 3 of our magnetism lessons. In part 1, we covered the basics of magnetism. Part 2, we covered the forces and fields around a current carrying wire and the different forces that can emanate from currents and wires due to the mix between electricity and magnetism, and that was a fairly lengthy lesson. This one I think will be a little bit shorter, but this finishes up the third lesson for magnetism. So what we want to do is start off with what we finished with last time, and that is the force on a current carrying wire. And so what we have in the picture in front of us is a wire connected to a battery, so there's a current running through it. And in this case, the current's running that way, and in that case, the current is running in the opposite direction. So on the left, it's going sort of into the page, and on the right, it's coming sort of out of the page. So the first thing that we want to do is want to take a look at, using the right-hand rule, just what the direction of the forces are. And you can see that by the pink arrows in the text below them, what the directions actually are. But we want to get good at using this right-hand rule, right? So remember that if I want to calculate the force, the magnetic force due to either a force or the current in a wire or a charged particle running through a magnetic field, I'm going to use the third right-hand rule, which is my fingertips point in the direction of the current. My palm points in the direction of the magnetic field, and therefore my thumb will point in the direction of the force. So in the first case on the left, my fingers are going to be pointing into the page, right? The magnetic field is going from left to right, so I've got to take and twist my hands like this, leaving my fingertips still pointing into the page, and my thumb is going to point in the downward direction. And remember, this is for positive current flow, which is the convention in circuits, okay? If we take a look at the right-hand circuit, what we have is we have a current coming out of the page. So now I've got to twist my hand like this, all right? Fortunately, my palm is already pointing in the direction of the magnetic field, and so the force is going to be up, right? Because my thumb is pointing in the upward direction, okay? So that's using the right-hand rule to figure out the direction of the force, which is half of what we need to figure out. The other thing that we need to figure out, and this again is the same kind of thing, it's a wire in a magnetic field and figuring out which way the force is going to go. So I'm not going to go through that, right? But we want to figure out what the equation, of course, for that force on the current carrying wire. And we went over this briefly in the previous section, and it is just going to be I times L times B times the sine of theta, and that's the angle between the direction of the wire and the magnetic field itself. I stands for the current, L stands for the length of the wire. Now this is not the entire length of the wire, this is just the length of the wire that's in the magnetic field. So for example, I could have a wire here that's that long, but a magnetic field, say, that's only like this, right? So I'll draw some X's over here for the magnetic field going into the board. Well, the length of wire that I would be interested would really just be between this point and this point, because that's the length of wire that's in the magnetic field itself. And then B stands for the magnetic field strength, and that's in Tesla, okay? Okay, so let's do a little example here. And what we have here is we have a wire loop. Right, so in the loop is in the shape of a rectangle, right? So we have a wire loop here, right? And it's in a rectangle, but only a portion of this loop is actually in a magnetic field. So we would like to know what the net force is on the wire due to that magnetic field. But we have 3 sections of wire that we got to deal with. We've got this one, we've got this one, and we've got the horizontal one. So let's think about this. In the case of the wire segment on the left, the current is going down. In the case of the wire segment on the right, the current is moving up. Right? So let's see if we can figure out what the force would be, the direction of the force on the left-hand side of the wire. So the current's going down. The magnetic field is coming out, fortunately. Otherwise, I'd have to turn my hand again. So the magnetic field, my palm is pointing out of the page. All right, my fingertips are pointing down. And so the direction of the force on the left-hand segment of the wire would be to the left. All right, so let me change colors here. All right, so the force on this segment of wire would be in that direction. All right, and now let's do the right-hand segment of wire. And so my fingertips are going to be pointing up now. All right, I'm going to have to twist my hand because the magnetic field is still coming out of the page. And which way is my thumb pointing? Well, hopefully you can see this. It's pointing to my right. And so the force on this segment of wire is going to be going to the right. So what are those two forces going to do? They're simply going to cancel each other out. Okay? Because the magnetic field strength is the same. The current running through them is the same. The length of the wire is the same. All right? And so the magnitude, the number that we would get for the magnetic field on this segment and this segment would be the same. Their directions are opposite, so they just cancel each other out. We don't have to worry about that part. Right? But we do have to worry about the bottom segment down here. Right? And we'd like to know what the magnetic field strength is going to be on that segment of wire. Well, it says that, actually it gives us the force here. It wants to know what the magnetic field is. So we need to calculate B. All right, well that's fine too. All right, so it tells us what the force is. It tells us what the current is. Right? The length is 10 centimeters. Right? So it gives us that right there. So it's 10 centimeters from this point to this point. So we know that. So F is, which is going to be 0.0348 Tesla, is going to be equal I, which is 0.245 amps, right? Times L, which is 10 centimeters or 0.1 meters, times B. So when we plug that into the old calculator, let's see what we get. And after plugging that into the calculator, I get 1.42, so B equals 1.42 Tesla, which is an enormously large magnetic field. Okay, so that is a very large magnetic field working on that wire. Right? So again, it's just FB is equal to I times L times B times the sine of theta. And in this case, theta was 90 degrees, so we really didn't have to incorporate that into the equation. All right. So let's try another example. In this case, what we've got is we've got a magnetic field that is going from the bottom of the page to the top of the page. All right, there's our magnetic field lines. And we've got a wire, and it does not tell us which direction the wire is, the current is going in. Oh, it does. It says it's going from right to left. All right, so it's moving in that direction. All right, so we have a 36 meter length wire, and it carries a current of 22 amps. So it's a pretty high amperage wire running from right to left. Calculate the magnitude and direction of the magnetic force acting on the wire if it's placed in a magnetic field with a magnitude of 0.5 times 10 to the minus 4th Tesla. So in other words, this is a high voltage wire that is in the Earth's magnetic field, and we want to know what the force is that's going to be on that wire. Okay. All right, so first of all, we can figure out what the direction of the force is going to be. Right? The magnetic field, right, my palm is going to point in the direction of the magnetic field, which is up. Oh, this is going to take some more work here. All right, and the current is running from right to left, so I've got it pointing that way. And my thumb is pointing into the page. All right, so it's going into the page, or minus C in this case. In fact, it says into the page. So we would like to figure out what the magnitude is. Well, again, we're going to use ILB times the sine of theta. So the current is 22 amps. The length of the wire in the magnetic field is the Earth, so the entire wire is there, 36 meters. The value of the magnetic field is 0.5 times 10 to the minus 4th, and the sine of 90 is just going to be 1. And when we plug this into the calculator, it's a relatively small force of 0.0396 newtons. Okay, so that's a rather hefty wire, and it would have a fairly small force on it, but it would have a force nonetheless. So a good question is why does the wire move? Why does the wire have a force on it, a magnetic force, just because there's a current running through it? Well, remember that early on we talked about a wire with a straight length of wire with a current running through it. What surrounds that wire? Well, the magnetic field surrounds that wire. And it's depicted here, right, on the left-hand side, right? You have a circular magnetic field at 90 degrees to the length of the wire, right? And you have the same thing over here. We have a battery attached to a section of wire on the right-hand side, and you have these circular magnetic fields that surround the wire. Well, guess what's going to happen if we take this wire with a current running through it that has now an internal magnetic field that is generated because of the current, and we put that into another magnetic field? Well, what happens when you have a bar magnet, north and south, and you put it next to another bar magnet, north and south, right? What are those two magnets going to want to do? Well, those two are going to want to repel each other, right? If I have this situation, right, south and north over here, south and north over here, what are these two magnets going to do? They're going to want to attract each other, right? So there's going to be a force in this case, there's going to be a force in this case. Well, now if I've got this circular magnetic field surrounding the wire, and I put it into another magnetic field, well, I'm either going to get a repulsive force or some kind of an attractive force, and that is the reason why that when I put a current carrying wire into an external magnetic field, there's going to be a force on that wire. All right, so we've said that there is a magnetic field that surrounds a current carrying wire. There's the current carrying wire. There's the magnetic field. But of course, again, this is physics, and we haven't said anything about what the magnitude of that magnetic field is going to be. All right, because if we want to calculate things, we want to do calculations, figure out what forces are. Say I've got a wire over here, and I've got another wire right next to it, and they both have current running through them. Well, they're each going to have a magnetic field surrounding them, right? And this is a horrible picture. It's supposed to be three-dimensional. But they're each going to have a magnetic field surrounding them. And those magnetic fields may repel each other, or they may attract each other, and we can figure that out. But if we want to know what the magnitude of the force is going to be, we'd be interested in having some sort of an equation, okay? So we know that the magnetic field is proportional to the current that's going to run through the wire, right? And the magnetic field is running in semicircles, right, in a perpendicular direction to the wire direction. So this comes into play, right? So the magnetic field is going to be proportional to I divided by 2 pi r, okay? And the only thing we have to incorporate into that still is some kind of a constant of proportionality that's going to give us, that's going to equate I and these values over here. And that turns out to be this constant mu0 here. And so the short of it is we end up with the equation at the bottom that's in the red box, is that the magnetic field, right, and it's called an internal magnetic field, it's internal to the wire. And that doesn't mean that it's only enclosed inside the wire, it just means that it's created due to the wire. The magnetic field is equal to mu0, right, and mu0 you can either use this or you can use this, and they are the same exact number, right? And that is Tesla meters per ampere. You don't have to remember that. All right, it's mu0 times I, the current running through the wire, divided by 2 pi r. Well, what this tells you is the magnetic field gets weaker as the radius, the distance from the wire, gets more and more. So the magnetic field, say out here, is going to be a lot less than the magnetic field close to the wire, and that should be to some degree, common sense. So let's try doing a problem here. Let's change the color of my pen here from orange to something else. All right, let's say that I want to find out what the magnetic field is. I want to know B. Whoops, I didn't change it. I want to know B. I still haven't changed it. All right, I'm not going to fight with it. If I am 5 centimeters from a wire that is carrying 3 amps of current. Okay, so I'd like to know what the magnetic field strength is going to be, right? So we can figure that fairly easily. So B is going to equal to mu 0, which is 1.26 times 10 to the minus 6th, times the current, which is going to be 3 amps, divided by 2 times pi times the distance from the wire itself, which is 5 centimeters or 0.05 meters. Right? So let me plug this into the calculator, see what I get. And I get 1.2 times 10 to the minus 5th Tesla. That's be a dot there. So 1.2 times 10 to the minus 5th Tesla is what the magnetic field would be around that current carrying wire that's carrying 3 amps of current. Okay. All right. All right. So here's another example. And on the left-hand side here, we have a current carrying wire, right? And it is going from the bottom of the page to the top of the page. Okay. So the first thing I want to know, well, actually, in this example, we have two things. I didn't even see this over here. We have a proton going from the bottom of the page to the top of the page as well. And what we actually want to know is we want to know the magnetic force on our proton due to this wire over here. Well, the magnetic force on a proton is equal to Q times V times B, right? So we have this, right? And B is the external magnetic field where the proton is traveling in. So first of all, what we need to do is we need to figure out what's the direction of the magnetic field where the proton is, okay? Well, the proton is to the right of the wire, right? So if I want to know what the direction of the magnetic field is, I'm going to have to use one of my right-hand rules. And it's the right-hand rule, I believe, number 1, where I use my thumb and then my fingers curl around. So my thumb is going to point in the direction of the current, which is going up. My fingers curl, right, on the left side of the wire out of the page, and on the right side of the wire back into the page. Well, the convention that we have is out of the page has dots, right, over here. Into the page has the crosses, right? So as far as we can now figure out the direction of the force on the charge due to the magnetic field that it's in, right? And so we're going to use the third right-hand rule, right, which would be the one with the fingertips and the palm using pointing in the direction of the magnetic field, and the thumb points in the direction of the force. Well, the magnetic field is pointing into the page, so my palm's going to point in that direction, right? My fingertips are going to point up, right? So this is an easy one for me, right? So fingertips pointing up, palm pointing into the page, and because this is a positive charge, we don't have to reverse anything here. My thumb is pointing to the left. So the direction of the force on the charge is going to be to the left. So the direction of the force is going to be in the negative x direction. So it's going to be pointing that way. All right. Now what we need to do is we need to figure out what the magnitude of the force is. Well, Q we know, right? That's just the charge on a proton, right? V, let's see. It has told us that it is traveling at 1,500 meters per second. So we know Q and we know V. We do not know B though, all right? We need to figure out what the magnetic field strength is from the current carrying wire. From that, we're going to use this equation over here, right? The magnetic field due to that current carrying wire is mu times the current in the wire divided by 2 pi r. Well, it says that we want to know the proton is 4 millimeters from the wire, right? So that's what we're going to use as the radius, right? That's the distance from the wire, so we can figure out the strength of the magnetic field 4 millimeters from that wire. So we're going to plug everything into this equation here, right? The value of the value of mu 0, right here. The current in the wire is 5 amps, and then 2 times pi times 4 millimeters. and we end up getting a magnetic field strength of 2.51 times 10 to the minus 4th Tesla, right? So it's a decently, a decent sized magnetic field. Now, what I'd like to know is I would like to know what the force is on the wire, on the proton itself, or the positive charge itself, right? So again, we have the value Q, right? So now we're using this equation, right? QVB. Q times the velocity times the value of B that we just got, right? We just calculated that, and we get the force to be 6.02 times 10 to the minus 20th newtons, all right, acting on that proton. So a fairly large force for a proton that has a mass of 1.67 times 10 to the minus 27th kilograms. So it's a pretty large force, so it's going to have a pretty big effect on that proton. All right, so now lastly, what about two wires that are next to each other? So let's say I've got a wire here and another wire over here, and they are both carrying 5 amps of current. And I'm going to label this wire number 1, this is number 2, and I would like to know the force on wire number 2 due to the magnetic field around the wire from number 1. Now let's also say that these are I'll make it 10 centimeters apart. Okay, so we know that. All right, so I'm going to have magnetic field lines around this wire, and one of these is going to be exactly at the point where this wire is, and it's going to be 10 centimeters away. So I can figure out the magnetic field strength due to wire number 1 that is acting at wire number 2. So B from wire number 1 at wire number 2 is going to be mu 0, right, times the current I divided by 2 pi r. Okay, so we're going to have B from wire 1 on wire 2 is equal to 1.26 times 10 to the minus 6th times the current. We said the current is 5 amps, divided by 2 times pi times the radius, and the radius is 10 centimeters or 0.1 meters. And when we do that calculation, let's see what we get. And this is just about 1 times 10 to the minus 5th Tesla. So that is the magnetic field strength at that point right there on wire number 2. Okay. Now, if we wanted to know the direction of that magnetic field, again, my thumb's going to point. We're going to use rule number 1, right-hand rule number 1. Thumb's going to point in the direction of the current, which is up on the page. My fingers are going to curl, so to the left of the wire it's coming out of the page, to the right of the wire it's going back into the page. So at this point here, it's going into the page. All right, so these are going to be X's. All right, so that'll help me to determine the direction of the force on wire number 2, which we can do right now before we even figure out the magnetic field strength. So the direction of the force on wire number 2, well, let's see. My fingers, this is right-hand rule number 3, fingers point in the direction of the current, which is up. My palm is going to point in the direction of the magnetic field, which is pointing into the page. My thumb is pointing to the left, so the direction of the wire here is going to be to the left. All right, so there's going to be a force that's going to want to push that wire to the left. How strong is that force? Well, it's going to be I times L times B times the sine of theta. Now at this point right here, theta is going directly into the page, so it's 90 degrees, so we know sine of 90 is just going to be 1. So it's going to be I, which is 5 amps, times the length of the wire. Well, we didn't say what the length of the wire is, so let's say that from here to here, the length is equal to 2 meters. All right, so it's going to be 5 times 2 meters. That's I times L. All right, I times L times B. B is 1 times 10 to the minus 5th Tesla. All right, and when we do that calculation, we get it's 10 times 1, so we're going to get 10 times 10 to the minus 5th newtons, or 1 times 10 to the minus 4th newtons. That's going to be the force acting on wire number 2 due to wire number 1. All right. So this can be done. It's just a two-step process. First step is figuring out what the strength of the magnetic field is at the position of wire number 2 due to wire number 1. So the position of wire number 2 due to number 1. We figure out that magnetic field strength, right? Then we can just plug that into the equation for the force on a current carrying wire, right? And that's just ILB times the sine of theta. All right, that is the end of lesson number 3 and the end of the magnetism lessons. I hope this helps. If you need more solved problems for magnetism, you can go on to my YouTube page, Doc Ontco Physics, and look at magnetism, and I believe I have several more out there. Again, hope that helps. Have a great day.